Let's get started. So today we will actually start the StatMech. Before doing that, I want to recap just a bit more of thermo. Some of the key concepts from 684, from thermodynamics, which will be, you'll see why they are useful. Okay. So the first thing I want to point out is let's imagine an experiment. Okay. So I will draw 3 axes. And let's say this axis is N, this axis is volume, and this axis is temperature. Okay. And in this space, you started your system at a certain point. So you have a chemical reaction. When the chemical reaction happens, you know at certain point, it has N1 number of particles, it has volume V1, and it has temperature T1. And now you are interested in some other state of the possibility for the chemical reaction where the number of particles have increased, the volume has changed to something else, temperature has changed to something else, right? So the question I ask of you is, if I draw a line here, which tells me this is the way the chemical reaction should happen, okay? And on top of this, I give you one more piece of information. I tell you what is the internal energy of the system at this starting point, E1, and I tell you what is the internal energy of the system at the at this point, E2. I don't want to call it starting or ending point. On this basis, can we say whether the reaction should go from point 1 to point 2 or point 2 to point 1? Why not? Why can't we say whether it's spontaneous or not? Huh? What do we need? So, okay, are you telling me that if I, instead of E1, and watch my words, listen to my words carefully. If instead of E1, I had S1 and S2, but no E1, could I then say whether it will happen? What do you think? So I'm not telling you both E and S. I'm telling you, if you only knew E1 and E2, or if you only knew S1 and S2, can you say which way will the reaction proceed? Why not? This seems doubtful.
No S, you can.
No, not in this space. In this space, you need to know A.
Yeah, you can use some other variable
That I'm removing, that you need to know that other variable, right? That's the whole point. So if your coordinates were N, V, and T, in order to decide whether a reaction is going to proceed back and forth, which direction the reaction will proceed with, you need to know the Helmholtz free energy. If you knew the energy and the entropy, then of course you know the Helmholtz free energy, right? And why is this true? This really follows from the fundamental postulate, which says that if you are working in the space of N, V, and E, then entropy tells you everything, right? Whether something is spontaneous or not. And that is something we did not prove. We took it in an axiom. I did give you some intuition into it. Remember, I showed you why should such an entropy function exist. We talked about shaking work and stirring work and things like that. So for those 2 of you who are new to this semester, if you go, I have left the 684 website open. In the first couple of lectures, there is a video and notes where I explain why should there exist a function S of NVE, which increases in the direction of spontaneous change. Right now, this is almost an axiom, but there was some intuition there, and we cannot really prove it. It's an axiom. The fact that spontaneity increases, that the entropy increases with spontaneity is, in fact, it cannot be proved. It really follows from how the universe was made. You know, everything was in the state of a big bang, and it continues to expand and things like that. You know, so we will really go crazy if we try to prove it. But it exists, and in NVE space, if you want to say whether a reaction is going to proceed forward or backward, you have to look at the value of the entropy initially and at the end. This is something, this really is the heart of 684, this page over here. If you remember this, everything will follow from here. That in NVE space, you have to look at S. In NVT space, S will not do, A will do, right? If you knew the value of A in the beginning and A in the end, then you can say which direction is going to be spontaneous. Okay, that's the whole point. Now you might say, oh, but if I knew E and S, I could construct A. But that's the same as knowing A, right? A is E minus TS. So you have to have that information. Okay. So any questions about this? Okay. So let's start once again and write this down mathematically. So 684 in thermodynamics, our point was there exists a state function. Actually, let me write it down. There exists, and I did not say anything about its uniqueness or what this function actually is. All I said is that it exists such a state function. There exists a state function S of NVE, which is thermodynamically complete. Even before this, there was even a more fundamental assumption. What was the even more fundamental assumption here? That equilibrium states of a system can be characterized using NVE, that equilibrium states exist, right? Why should equilibrium states exist? That's yet another philosophical question, which is thermodynamically complete. And partial S by partial, all its partial derivatives have to be positive. Why should the first one be positive? Because S is extensive. When we say there exists a state function, I also say there exists an extensive state function. So S is going to double if you double N. So partial S by partial N is trivially positive. So these three things exist, and this particular one, that S as a function of E at constant V and N is positive, allowed us to proceed further from here, right? So anyone remembers that if the slope is, what does this mean? This means S increases as a function of E. That can happen in three ways. It can happen like this, it can happen like this, it can happen like this. Anyone remembers which one is correct? Go ahead.
It's the bottom.
What is that, the concave or the convex one? Everyone agrees? Are you sure it's the bottom one? I would like you to think about it.
Of the axes.
S and E.
That's it.
So which one is correct? This one or this one? It's the bottom one. And statistical mechanics, when we do our first ensemble, you will see that it's actually logarithmically. That's almost a postulate. There is a reason why it is bottom one, and log shows up sooner or later, Boltzmann's formula. So, but the fact that it is monotonic means that at any value of S, you have a unique value of E, right? If it was non-monotonic, this problem would be difficult, which means that if S of NVE is complete, we can swap these two out and also think of E as a function of NVS. Now this is thermodynamically complete. So if I go back to this picture on the first page, and I drew a similar graph over here, where the coordinates were N, V, and S, and you knew the values of these two things at the initial and the final point, at point A and point B, then looking at the value of internal energy would tell you which direction you're going to proceed in. So it's all about coordinates. Which coordinates are you looking at? No state function, no free energy on its own is going to tell you which way a certain chemical process or biological process is going to happen, unless you know what are the conditions under which you are studying. Okay, so if you're, and this becomes super practical. If you're designing a battery material where there is a semi-permeable membrane, right, and matter can flow in and out, that's a very different condition than something happening inside a furnace, right? Every time the conditions change drastically, which is very different from an open container. So you always have to think about condition, then think about free energy. Now you might say, why should one ever care about constant entropy as a parameter? It sounds abstract, but you will see sooner or later in your research, there are conditions where you can actually control entropy. I can't think of any top of my head, but they show up. So with this, we can now, anytime something is a function of three things and it's a state function, we can write down its total derivative, right? We don't need to worry about the squiggly partial. So ds is going to be partial s by partial n at constant VE multiplied by dn plus partial s by partial v at constant NE multiplied by dV plus partial s by partial E at constant NV multiplied by dE. Similarly, dE is going to be partial E by partial N at constant Vs multiplied by Dn, partial E by partial V at constant Ns multiplied by dV plus partial E by partial S at constant NV multiplied by ds, right? And at this point, we showed, and you did this in your 684 Foster second homework set, that why this thing is actually chemical potential, which we can measure in experiments and control. While this thing is minus P, it is minus times the pressure, the gradient of energy with respect to volume. And this thing is temperature. So that is the most unique thermodynamic definition of temperature. Of course, if you go on the road and tell someone, oh, today it looks like the partial derivative of V with partial derivative of S at constant N and V is really taking a dip, they will punch you, right? But that is the most rigorous definition of temperature. Now, as per our postulates in thermodynamics, what can we say about temperature? Can it be positive or can it be negative? The monotonicity tells us that the temperature must be positive, right? This is however true only in the thermodynamic limit. Thermodynamic limit means lots and lots of particles, n tends to infinity. You will see some counter examples in StatMech where temperature becomes negative. And you can measure it in a lab. And the funny thing is, negative temperature is hotter than positive temperature. It's true. You'll see that homework problem. Who here is working on like quantum systems? No one? Yeah, quantum material. Yeah. So, you know, there was a professor here, Chris Monroe, and I would have students from Chris Monroe's lab, and they would always be interested in that because they could create systems, you know, when you're doing quantum computing and things like that with a few qubits, and it's not thermodynamic limit, and there everything goes crazy. So we have this. So this relation where we have introduced these three terms can be written down as dE is equal to mu dN minus P dV plus TdS. And this is known as the integrated first and second law of thermodynamics. This includes all information. You could have written down similar things for ds also, right? Or for other variables. So this one is very useful. Now the question is, we know that E has natural variables NVS, and if we were to write down E as a function of NVT, there is nothing wrong in it. You can write down such a function, but it is thermodynamically incomplete. What does it mean? It means, once again, I will re-emphasize this point. It means that in NVT, if I told you the value of E1 here and the value of E2 here, you cannot say whether the reaction will proceed in this direction or in the back direction, right? E does not contain that information. The question then is there a variable which, when viewed as a function of NVT, does contain that information? I already told you that's Helmholtz energy, the Helmholtz free energy, right? So let's show that is actually the case. So there are two ways of doing it. One way of doing it is to take the Legendre transform. If you have E as a function of NVS, you can write down E minus, you want to remove this variable and replace it with this one. So you write down E minus partial E by partial S at constant NV multiplied by S. So this is the Legendre transform of E. This has a name A, and we defined this one as temperature, right? This was our definition of temperature. So A is equal to E minus TS. If you look at it, A is equal to E minus TS, it looks like, wait, you didn't get rid of S. it would almost look to you that maybe the natural variables for A should be E, T, and S, right? But it's not true because, and in order to really prove that is not true, let's write down dA. So in order to see the natural variables, you really need to write down the total derivative and see what's going on, okay? So let's work with it. dA is equal to dE minus TdS minus SDT. What is dE? We use this formula. Mu dN minus PdV plus TdS, then this one minus TdS, then final one minus SDT. So plus TdS minus TdS cancel out, and we are left with mu dN minus PdV minus SDT. So you can see the total derivative of A depends on partials of N, V, and T. Therefore, the natural variables of A are N, V, and T. Okay? The Laurent transform already tells you that, but here you can see for yourself. And this way, we introduced many other state functions for all other forms of variables. And the reason we wanted to do that is because we said controlling entropy in an experiment is going to be hard. Measuring entropy in an experiment is going to be hard. Measuring temperature is easy, right? So, and in general, measuring intensive parameters, sometimes, not in general. I would argue that measuring chemical potential is harder than measuring number of particles, right? Chemical potential you can write down. Some of you even say you like the formula so much, you mentioned it as like a favorite equation, but chemical potential is still abstract, right? And N is more intuitive. So you have a way of changing. Anytime you have three, you can almost think of a menu now where you have N, V, and E. These three are extensive, right? And their corresponding intensive parameters or conjugate parameters are mu, pressure, and temperature, right? So you can work with any three. You can work with NPT. You can work with mu, VE. You cannot work with N, mu, and T. That's completely, why cannot you work with, why cannot you have a description of equilibrium that includes, we said equilibrium can be defined by three variables, right? So why cannot we define equilibrium using N, mu, and T? But what is it missing? It's missing mechanical equilibrium, right? You're correct, it is derivative, but more fundamentally, it's completely missing out of information about volume and pressure. What is equilibrium? Equilibrium is a state of material equilibrium, mechanical equilibrium, and thermal equilibrium, right? So you need to have one variable from at least each column. Otherwise, you have no way of talking about equilibrium along that. True equilibrium means all three things, true containment. You can think of it that way. So in other words, when your control parameters are NVE, so now I will not go through all the state functions or other Laurent transforms. I want you to do it yourself. And even if you took 684, it's a good way to recap things. If you have control parameters NVE, the relevant state function that is thermodynamically complete for NVE, which one is it? Entropy. Let's start adding more. NVT is Helmholtz energy, right? Which else do we have? Which one is it for Gibbs? NPT. What about enthalpy? He remembers. I think I might have even had a dream one night where I was like walking somewhere and all of a sudden you show up and go like the natural variable for enthalpy or SP. And I'm like, why would anyone remember that? You do, great. Anything else? Huh? Well, do you remember the names of the corresponding thermodynamically complete state functions? Energy is envious. Is that what you are saying, Kinjal?
Yeah.
Well, that's of course. And anything else? Yeah, what is it for grand potential? Grand potential, which is defined as minus PV. What are its natural variables? UVT. Good. So this slide or this page will play like supreme role in 687. Okay. And this is where I think it's good to have done thermal properly. It makes StatMech actually very easy. You will see. And the reason it becomes very easy is, as next thing we are going to do now is to start talking about ensembles and all those things, all the good stuff. You will see that anytime statistical mechanics tells you what is it that is being enforced on a system, you have to go and think about its corresponding state function that is thermodynamically complete. You have to write down the partial derivative involving that state function, and then you're set. You can calculate everything of interest. And this is what we'll be doing again and again and again. If it does not make sense right now, don't worry, it will soon. Any questions about this? Okay, so let's now actually start with StatMech. And I want to remind you once again that thermodynamics is true in the limit of thermodynamic limit. You know, it's almost a cyclic answer. So thermodynamic limit is when thermodynamic holds true. And what is the meaning of thermodynamic limit? N tends to infinity, V tends to infinity, while the ratio, which is known as the density, is finite. It might change, but it is finite. Okay, this is the thermodynamic limit. What we are going to do next, we are going to go away from the thermodynamic limit. We will talk about finite size systems in finite volumes, but we will always check our results. Statistical mechanics should reduce to thermodynamics in the finite size limit. You know, it's just like classical quantum mechanics reduces to classical mechanics, right? In some limit. If it does not, then it's wrong. There is nothing. Relativity reduces to classical mechanics, right? So let's keep this in mind, and then let's start with statistical mechanics. So now we are really starting 687. Okay. In order to do 687, so far in thermodynamics, we really thought about macroscopic variables, right? We thought about volume, pressure, things like that. In statistical mechanics, we are going to, and so that was a low dimensional space, right? We thought about 3-dimensional space. In statistical mechanics, we will start with a very, very, very high dimensional space. This space is known as phase space. If you have an n particle system, phase space is made up of the coordinates of each particle, okay? So R is going to indicate the coordinate, the position of every particle. It's a vector, but I will just use R, okay? So R1, R2, and total, you are going to have 3n such numbers, right? We are working in Euclidean space, so every particle has 3 coordinates associated with. Similarly, you are going to have momentum for each particle, and P is not to be confused with pressure. I mean, it will happen, but it will be clear from the context. The reason it will be clear is because it's very rare that for pressure, I will put a subscript. For momentum, I will almost always have a subscript. So P1, P2 till P3n. So this is position coordinates, and these are our momentum coordinates. And together, we have a 6n dimensional vector. In thermodynamics, it did not make sense to talk about this because n was infinite, right? We could still have talked about it, but it would take a lot of memory, right? It's infinite space. Here, n is finite, so we can talk about this. So our starting point in statistical mechanics is to draw this 6n dimensional space. Now, I don't know how to draw even 4-dimensional space, right? So I will just draw a 2D space, okay? And we will just imagine from there. So let's draw it, where this axis is R, this axis is P, but in reality, what you have is, there is actually yes. In reality, there are lots and lots of coordinates, right? So this one could be R1, this one could be R4, 5, 5, 7, whatever it is, right? So I'm just going to draw two, P and R. So the macroscopic state of a system, and we are doing equilibrium statistical mechanics, okay? So I will not say at equilibrium all the time, because that is something we are never going to get out of. We are always in equilibrium. Even in statistical mechanics, things have equilibrated, there is not much interesting happening, but still a lot of interesting things happen. The macroscopic state of a system, how many variables do we need to characterize a macroscopic state? 3, right? This was the first postulate in Callan, right? It could be NVE, for example, right? So this can be characterized using NVE or some other 3 variables, right? It could be NVT, that characterizes the macroscopic state, or NVT, ... Today, we are also going to talk about the microscopic state of a system. And the microscopic state of a system needs 6 n numbers to characterize every coordinate and every momentum of every atom in the system. That is your microscopic state. So macroscopic state is 3-dimensional, while the microscopic state is 6n dimensional, and it needs R1, R3n, P1, ... P3n. Okay? Yeah.
Aren't we saying, so the macroscopic state, we don't consider time dynamics at all at equilibrium, but we're looking to describe the microscopic state, you're using momentum, which is time-dependent quantity.
Yeah, that's where ergodicity will come and help. Yeah, things will be consistent. Don't worry. He's already getting sad. It will become consistent. That's why we need ergodicity. Yeah. So, yeah, but very good point. I mean, you're looking at momentum. Why do you have time? Why are you saying that time is ignored? So, what it means, so a simpler way to answer your question is that many microscopic states could correspond to the same macro state, right? The whole idea of a macro state is that the details of these micro states don't matter. That is the whole idea, right? So this 6n dimensional space, there can be so many gazillions of values which correspond to the same macro state. That's why time does not matter. Equilibrium is, for construction, the state where you don't need to account for all these things. But in statistical mechanics, we will. And why we will? Why will we do that? I don't know. It will be fun. And it also turns out to be very useful. So now let's think about the trajectory of a system in phase space. So we have P and we have R. Again, I'm drawing only 2-dimensional, but every P is actually 3n and every R is actually 3n. So it's 6n dimensional. So let's say we start at some point 1. It has a certain position. It has a certain momentum, right? It's going to go somewhere. Let's say it goes here. And let's say then it goes, so it went to point 2. Then it went to point 3. Then it to point 4. And it keeps doing this and this. I know Vanessa loves classical mechanics. So Vanessa, tell me, can such a trajectory, as I follow it in time, do this? Can it cross back on itself in classical mechanics? Classical mechanics is deterministic. If it crossed back on itself, we will have a fundamental problem, right? The fundamental problem would be that if you were at, sorry, I erased it. If you were at this point over here, you wouldn't know which way you are going to go, right? You might go this way or you might go this way. So phase space trajectories for a classical system cannot intersect on itself. Okay, so a good, so classical mechanics, and the point to keep in mind here is classical mechanics in phase space. Any time you're missing out on a degree of freedom, if you forgot to account for a single of those 6n momentums, or a single of those 3n momentums, or a single one of those 3n positions, then this is not true. So trajectories do not intersect each other only in phase space, and phase space is exactly 6n dimensional. If you reduce the dimensionality by 1 or 2, forget about 6n, even just 1 or 2 were missing, then this guarantee is lifted. It's not going to be true. So classical mechanics in phase space is deterministic, which means that a trajectory that starts, it could come infinitely close. And in fact, if you observe this system long enough, it will come infinitely close. It has to come infinitely close. That is ergodicity, actually. It has to come infinitely close, but it will never intersect. Intersections will happen if this is not 3n dimensional. Intersections if P is not 3n dimensional or R is not 3n dimensional, okay? Anyone remembers Liouville's theorem from there? Yeah, go ahead.
I just don't understand why it can't intersect. So what is the problem if it's intersected? So
The problem is that when you write Hamilton's equation of motion, which one is it? Minus Q or plus Q? I always forget. These equations are deterministic. When you start with a certain value, they will go to the same next value. But here, if you started at this value, one of them could go here and the other one could go here. That's a problem. So this equation has no noise. Everything is gone. So if you start from, it's like integrating from a certain boundary condition and getting 2 different values. That does not make sense, right? That's the whole idea here. Anyone remembers Liouville's theorem?
Volume element phase space will cover the entire phase space, something like that.
Something. That's not really
Its
mathematical.
volume doesn't change, but its shape can.
Yeah. So Liouville's theorem, which we are not going to do here, concerns how these trajectories behave, how their volume, how they look around in space and stuff like that. We are not going to get into that, but the thing you need to remember is in classical mechanics, they are not going to intersect. If they intersect, it means that you're missing out on some degree of freedom. The other reason they might intersect is quantum mechanics. Yeah, go ahead.
If you're missing like just a single.
Yeah, it's game over.
Can you just, well, why can't you just make it relative coordinates instead? Like shift everything relative to relative? Because
Well, you can make relative, but you're making further assumptions about what is the system doing as a whole and things like that. So if the center of mass is not moving, then sure, you can do relative coordinate. But that's additional information, right? So you don't have that. But there comes quantum mechanics. What does quantum mechanics say? Quantum mechanics says that you cannot have an infinite resolution. Quantum mechanics says that the highest resolution that you can have is limited by Planck's constant, right? That delta P multiplied by delta R is something like Planck's constant. And I always get whether is it H or H bar? Doesn't matter. It's 10 to the minus 34, right? It's a very, very small number. Quantum mechanics says that inside this box, it doesn't matter. You cannot pinpoint where you are. And quantum mechanics is part of the origin of chaos. That when trajectories come into a certain box, they really don't know what's going on. And anytime they are inside that resolution, now from here, they can go wherever they want. And if you're interested in more in this topic, I really recommend looking up videos by this guy, Leonard Susskind. He is at Stanford. He has a lot of very nice videos on statistical mechanics on YouTube where he talks about these things. And like, yeah.
Can you have completely closed paths in a phase space?
What does that mean?
Like a circular loop.
Sure.
You're not violating the crossing over thing, but you.
Oh, no, not in phase space.
But if I remember correctly, when you're looking at a harmonic oscillator
Mhm.
in the PQ space, you have closed loops depending on the energy of the oscillator itself, right? That it spaces out.
But
more.
not in phase space. So the thing is, think about what is a harmonic oscillator? Harmonic oscillator is, let's think about it simply. It's just a swing, right? And the fact remains that if you run the swing long enough, it should stretch out and go wherever you want. You know, the extension should become longer and longer, longer, longer. You just didn't wait. So even in a harmonic oscillator, but what you're saying is it should lie on a ellipse like this, right? Yeah. I think that's okay because this is not violating the intersection. Closed is okay, but you cannot have something like this. So harmonic oscillator, and we will get to that actually in a moment. It's good that you brought it up. We will be drawing some trajectories in phase space. So harmonic oscillator has that is why I did not make any claim about how much we are going to cover in this. That depends on the physics of the problem. But my claim that you are not going to intersect each very well, that is true even for an harmonic oscillator. This cannot happen.
But the thing that I find
Yes.
surprising is you can jump in energy states, at least at a quantum level. So you can jump from one curve to the next curve without technically intersecting or violating the rule that you're. But
We have to be careful if we are writing out all the coordinates there. Okay, so what is causing the jump? Is there something driving it? Like, we will do a bunch of quantum, so don't worry. Okay, we'll get there. Any questions? So all of that will become clear. When you're jumping, what is happening to the total energy? So anytime in this course, when we talk about any microstate, the first thing we have to talk about is, what do we know about the macrostate? What are we working under? So the thing that you're describing to me, is it a constant energy experiment or not? We have to start with all that carefully, right? So if it's really jumping, what is happening to total energy, where it's coming from, right? So we'll work carefully. So keep this in mind, that this is a phase space trajectory, which is complicated. It cannot intersect on each other in classical mechanics. In quantum mechanics, it can. But now, if we had some property of a system that we want to calculate. So when we do an experiment, any real lab, like how many people here do actually experiments, like not simulation? More than the simulation types. That's good. Anytime you do an experiment, you are actually following a system in phase space. That's what you're doing. You're not noting down all coordinates, because that would be kind of crazy. It will be Avogadro number of atoms. But what you're doing is you start your system here, right? And then something happens to it. It comes over here, it goes over here, it goes over here, and it keeps moving. You don't trace out this trajectory, but what you actually do is, let's say you wanted to measure the average energy. Let's start with the simplest one, the internal energy of the system, right? You make a measurement over here, you call it E1. You make a measurement over here, you call it E2. You make your measurement over here, you call it E3, E4, and you keep doing it, right? And the value that you measure in an experiment of any observable O, it could be energy, it could be anything that is a state function, okay? O is any state function. Is given by you making capital M number of observations. So you started at E1, E2, E3, E4, and let's say you went till E capital M, okay? And averaging it out. This is what we do in an experiment, or you do in an experiment. I do simulations mostly, but you can do this in a simulation too, right? You just run a simulation and you measure things as a function of time. And you study its fluctuations and you say, okay, now it has equilibrated and I have my particular value of this thing, right? So this is the time average of that observable. Which brings us to the concept of the ergodic hypothesis, which I mentioned earlier, and now we will look at it again, or the assumption of ergodicity. And this here is our first key assumption in statistical mechanics. So in thermodynamics, we had a bunch of them, right? There exists this equilibrium state, which depends on 3 variables. Then we said there exists a state function which characterizes them, right? All those things. Here, this is the first assumption we are making. So far, we have not made any assumption, but now we are making one, which is that time average is equal to ensemble average. So let's try to understand what is this ensemble and what is this ensemble average, and why is this assumption useful? And we cannot prove this. There is no way to prove the ergodic hypothesis. You can prove it in certain limiting conditions if you assume certain types of, if you assume a certain Hamiltonian that connects the P and R, then you can prove it, but I don't think it's proved in the general setting. So let me draw that picture from last page once again, where I had my R coordinate and my P coordinate, and I had a trajectory that went something like this, Maybe it's a closed trajectory, I don't know, but it's not going to intersect each other in classical dynamics. And I have 0.1, I have 0.2, I have 0.3, and I measure the value of the observable here, O1, O2, O3, and average it out to get the value of this observable. Ensemble average says that instead of following the trajectory for a very, 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 very long time, let's do an experiment. Let's create a gazillion different copies of the experiment, okay, and run it for a very short time, basically instantaneous, no time. Just create different copies, and I will draw a little jiggle at every point, but you don't even need to have the time there. You just create the copy. All the reason you need time is yeah, let's not get into that too much. So we create many, many different copies of the system, completely independent, okay? And they are not talking to each other. And we study them. And then we measure the value of O in copy number 1, in copy number 2, in copy number 3, so on and so forth, and average this out. So these copies that we created, these copies of the system comprise an ensemble. An ensemble really means a collection, right? You have created a collection of states, a collection of microstates, okay? Consistent with the macro state. Okay, so we have some macro state. Maybe it is given as a function of NVE, maybe it is given a function of NVT, mu PT, whatever you have. If you're like Nathan, then your macro state is probably given as a function of NPS, sorry. So you have that macro state and you go and create lots and lots of copies of the system, and you will have to create a ton of copies, like very, very large number of copies. And statistical mechanics will show you procedures to check whether you have enough copies or not. And now you calculate the average in this setup that is going to be known as the ensemble average. So let's become more mathematical about this. So time average was 1 over m, let's call it t. T is equal to 1, t is equal to m, and the value of the observable at that time t, right? It's just an index. I changed I with t. Ensemble average is kind of similar. It is also going to have a summation, but now the summation will be over nu, the Greek letter nu, which we are going to call the index of the microstate. Okay, because each of these configurations that you created over here, that's a particular microstate. Okay, so that is the microstate index. In each microstate, you calculate the value of the observable. Now there is something which is super critical, which is the probability of that microstate. Is that microstate going to happen or not? So let's go to the example that Vedant mentioned, which is when you have, yeah, it's great that you mentioned it. That will give us some intuition. I will wait for just a moment. We're going to the next page. Yeah, go ahead.
Yeah, so if the system's connected to like, it's like a test tube in a bath.
Mhm.
So the temp energy is fluctuating.
Mhm.
Aren't you ignoring degrees of freedom, and does the trajectory crossing?
You always have to consider system plus bath for this to hold true. Nothing can be ignored. If there is a bath, you have to account for everything in the bath. So that's it. There will be a lot of, there will be lots of baths in this course. So what is this P nu? Let me write it down again on the next page. So statistical mechanics, by the way, starts kind of abstract, just like thermodynamics. It starts abstract. Like what are these averages, blah, blah, blah. Then it becomes very hands-on, lots of calculations and stuff. But these abstract bits are very important, especially understanding ergoricity. There are really only two key assumptions. One is ergodicity and the other one connects to calculating P nu in an isolated system, which is known as the assumption of equal a priori probabilities. And we'll talk about that in just a moment. These two assumptions, that's it. Everything follows from there. So let me write down the ergodic hypothesis. It says that the value of an observable can be calculated by summing its value over time or doing an ensemble average where we go to a given microstate characterized by nu, calculate the value of that observable in that microstate, O nu, and we think that will take all our attention in the coming semester. Basically, it's all about calculating P nu from here on. So let's see, what is this P nu? This is the probability of finding the system in a microstate nu consistent with macroscopic information. Okay. Let's go to Vedant's example. Vedant's example was a harmonic oscillator. Okay, let's make it a simple. I'm going to call it Vedant's. Did I spell your name correct? Good. What is the meaning of your name? It's like end of knowledge or something? Wow. He's the end of knowledge. You know the meaning of my last name? Tiwari is a, I know I'm going on a tangent, but Tiwari is a, what do you call it? Like a distorted version of Trivedi, which means three Vedas. So I'm supposed to have mastered 3 of the 4 holy books. I don't know which 3 though. Anyway, let's come back to this. So Vedant's example was a harmonic oscillator. Okay, there is a spring and there is this coordinate x, and you have the speed along this momentum along this coordinate p, right? This was your example. And you are just, you pull it, it comes back, and you push it, it goes further away. So in this case, and there is no bath, there is no temperature, there is nothing, you know, it's just going back and forth. If I was to draw, how would I draw the phase space trajectory of this one? What can we say about a harmonic oscillator undergoing oscillations without anything else? What is its kinetic energy? P square by 2m. What is its potential energy? Huh? Half kx square. What can we say about its sum? It's constant. Does everyone agree with that? Right? There is nothing else going on. There is no friction, there is nothing. So T plus V is equal to constant. That is P square by 2m plus half kx square is equal to constant. How would this curve look in my phase space? What is this an equation of? Ellipse, right? So it's going to look something like this, right? That's it. So this is your phase space trajectory. It's stuck. It has to move on this. So now if I asked you to tell me the microscopic state probability, P nu, for a given microstate, what is the probability of this microstate over here? 0 for this red one. What is the probability of this microstate over here? Everyone sure? It cannot happen. So the only microstates that have a certain probability are the one that lie along the curve. And what is going to be that probability? Can we distinguish one of them from the other one? So what will be mathematically that one? Okay, but that's one way of thinking of it, but I would just call it 1 divided by total perimeter of the ellipse, right? And I'm being a bit sloppy in the dimensions, but total number of microstates. And this something, so this example should make sense to you. If this makes sense to you, then StatMech is going to be easy, because microcanonical ensemble, which we're going to do next, is basically just this thing. So this microstate is not allowed, because we saw that for this particular system, p square by 2m plus kx squared by 2 is equal to constant. This microstate is not allowed. The only microstates that are allowed are the ones that lie along the line, right?
Are they energy microstates? Shouldn't they be energy microstates?
Microstate is microstate.
No, like, because you can have different values of P and X that lie on that same curve.
Sure, all are equally likely.
So how is it P mu? There is one by the, because each point on the ellipse is defined by 2 coordinates, the momentum and the.
But each of them is completely likely. Doesn't matter. On my harmonic spring, imagine a swing. I could be sitting in the middle of the swing, or I could be high up there. Both are equally likely. But that is actually what happens on a perfect swing, right? Did anyone try a swing recently? There's one in Berlin. You can go and try it. And if you don't have any friction, the amount of time you spend in the middle of the swing is the same as the amount of time you spend at the highest point, right? It's friction that screws things up, but the amount of time is the same. The probability of observing you is the same. So this is an example of how a microstate probability is calculated. And just to emphasize how important this is, I will write down in words in the next page. Statistical mechanics is all about calculating P nu, or microstate probability distribution given what we know about the system macroscopically. This is all there is to StatMech. Yeah, go ahead.
So you said that for microstates, the probability for that harmonic oscillator is marked by the perimeter of the
Mhm.
right? But we know that there are infinite microstates, right? For the harmonic oscillator.
Mhm.
Right? And so so the total probability of all the microstates should come up to 1. But
If you're thinking about infinite microstates, then you don't have to sum, then you have to integrate. And that's where his delta function, Patrick's delta function thing comes into play. So what I'm describing here is to think, maybe it's not infinitely many microstates, maybe I'm assuming that they're tiny blocks defined by your instrument resolution, for example, right? If it's really infinite, then you have to think about P nu, D nu type thing, right? And then you have to be careful. So anytime the infinite things happen, it's because you're not thinking about continuous limit, you're thinking about discrete. Yeah, go ahead.
Does, assuming that all the probabilities along the ellipse are the same, come from ergodicity, or is that another?
Good point. That's the second assumption. Excellent. Second assumption. So the first assumption was ergodicity. And the thing I'm going to write down next is not implied by ergodicity. Ergodicity does not tell us that. This is an assumption I am making. I have no way of proving it. If I didn't do it, I wouldn't have any way to proceed. And once I write it down, I will try to tell you why it kind of makes intuitive sense. So the second assumption in statistical mechanics, which cannot be proven from ergodicity, is known as the principle of equal a priori probabilities. A priori means, what does a priori mean? What language is it? Latin, right? What does it mean? A priori is before, right? Without any assumption. It is an assumption. So beforehand, what do you know? So beforehand, if you know nothing about a system, there is a principle that tells you all probabilities are equal. What does it mean? It means that, what does this principle really say? It says that an isolated system has all microstates equally probable, consistent with total NVE. And we are going to spend a minute trying to understand this. This is a heavy statement. It looks kind of obvious. When you try to think about it, you will get a bit confused. So an isolated system, I have a cup, I close it, okay? Its volume is fixed now. Nothing can escape out of it. The lid is really, really tight. Maybe, is this someone's bottle? Or is it a gift for me? Maybe someone left it. So this is better, right? It's tight, right? It's probably insulated. No energy can go inside. Its volume is fixed and no mass can exchange. But you do know that even though the number cannot exchange, number of particles cannot be increased inside and outside. That means there's a fixed number of particles, right? Some number n. Maybe you know what it is, maybe you don't know what it is. Because in order to know what it is, you will have to open it and check, right? So maybe you somehow know what it is. Same thing for volume, right? You know what it is and it is not going to change. Same thing for energy. So the reason I said this will confuse you once in a while is because for volume, you can say, okay, maybe I can check the volume without doing anything to it. But how do you check the volume of anything? Can you check the volume without? So the point I'm making is almost philosophical. How do you check the volume of an isolated system? Huh? It's isolated, so you cannot do anything. You cannot probe it in any way. But if it was a perfect cylinder, I could just make some measurement, right? And measure the volume. So you have to imagine you do something similar for the energy and something similar for the number, right? And why do I use these three to describe an isolated system? Because these are our three starting points in thermodynamics, right? Isolated in terms of particles that can go in and out, isolated in terms of volume that can change, isolated in terms of energy, right? So thermally, mechanically, and chemically, this system has nothing to do with the universe. And this second assumption, the principle of equal a priori probability, says that under such a case, all microstates that happen to have this n and this v and this e are going to be equally likely. Why does this assumption make sense? Because you have no way of probing the system. It's isolated. This is all saying that if you didn't know anything about the system, you can't do anything. You have to assume, right? There's no other way. Why? There is no basis for you to say that higher energies might be less likely than lower energies. How do you know that? You cannot do anything to it. I don't know what's going inside it, right? All I can say is that if you tell me a microstate where the volume of this thing is double, that's not possible because I know volume is given. And if someone told me that the number of particles here is 1 mole, and if you tell me suddenly it has 2 moles of particles, I know that is not possible. But any particular point in the 6n dimensional space, which has this number of n, v, and e, is going to be equally likely. I have no way of saying which one is more likely than the other, right? So this is the equal a priori probability. We can write it down more mathematically. Let me do that on the next page. This means that P nu, the probability of a microstate, is constant if the energy of that microstate is E, if the volume of that microstate is V, if the number of particles in that microstate is N, and it is 0 otherwise. Everyone okay with this? Yeah, go ahead.
The contradictory to second law of thermodynamics.
No. I haven't introduced any entropy here. What is the contradiction? Tell me.
I mean, it means like random distribution.
What is random? Define random. Have you seen Kung Fu Panda? Come on, then my reference is terrible. You should watch. I think all of you should watch Kung Fu Panda. It's an inspiring movie. Some people have said, right? So I'm like that master there, and you're the panda. No, the panda is very good because So you have to ignore all prior knowledge. What is random? Tell me. I haven't defined it. There is no contradiction. You will see. It's really consistent with.
We assume that nonsense distribution is equal to all the particles shape your study.
Yeah, but instead thermodynamics, we haven't talked about microscopic distributions. We haven't talked about probabilities of microstates. There were no microstates in thermodynamics. Thermodynamics was pre-Boltzmann, right? There were no atoms even. So the concept of a microstate was not there in thermodynamics. This is the first time we have started talking about it. And you will see there is no contradiction with second law, because next class we are going to define the entropy in such a way that there is no contradiction, just to solve that problem. Yeah, but good point. And watch Kung Fu Panda. All same, all perfect. Okay. Where was I? Yeah. So this is constant, but we can go one step further. We can actually give it a number. Okay. In order to give it a number, I'm going to introduce a symbol, omega, capital omega, which depends on NVE. And this symbol is super, super important. Its name is microcanonical partition function. It sounds very complicated. If you haven't seen it, you would be like, why would you call it such a complicated name? And whatever this thing, first, I don't know what this thing is. And why would you give it such a complicated name? The reason why it is called partition function will take some time for it to become clear. But for now, let's just, you could have called it LX, doesn't matter, but this is just a name. Okay, we stay with it. Go ahead.
What makes this different than S? Because it has the same natural variables.
Yes. It'll come. You don't know whether it is extensive or not yet. So we are running ahead of ourselves. We will see next time that S is actually log of this thing. Okay, that's the only thing. It behaves like S, but S is related to this logarithmically. So we'll get there in a moment, next time. So microcanonical partition function is defined as the number of microstates a system can have with n particles, V volume, and here comes the interesting one, energy E between E and E minus delta E. This is the definition of the microcanonical partition function. Okay, so we are calculating the number of microstates a system can have with consistent with n particles, volume V, and energy between E and E minus delta E. Okay, if you have this, then we can write down the value of P nu in terms of this omega. So if every microstate is equally possible, and you know the total number of microstates, right? And let's not worry about what Kinjal said about the continuous thing, because all you have to do there is to replace the summation with an integral. Okay, so for now we can say that P nu therefore must be 1 over omega of NVE if for all microstates that follow what we wrote down over here, right? All microstates where number of particles is n, volume is V, and energy E is between E and E minus delta E. The number of microstates, the probability is going to be P nu is equal to 1 over omega, right? Because all of them are equally likely, and if there are omega of them, then the probability is 1 over omega. And it's going to be 0 for all other microstates. I'm going to say just one more thing and then stop. And next time I will start from this point over here. Normally in math, when we define probability densities, we say P of X is the probability of finding a variable between X and X plus dx, right? And we say that dx must be small, right? Otherwise it does not make sense. For this one, actually the choice of delta E really does not matter. You can make delta E bigger and bigger and bigger and bigger and bigger. It does not matter which delta E do you take. And the reason for that is phase space is very, very high dimensional. It's so high dimensional that the volume of anything. So let's let's imagine surfaces in different dimensions, right? So in 1D, what is the simplest surface you can imagine? A line, right? It starts from a point and goes to a point. Now think about the ratio of the circumference of this line divided by the area of this line. In this case, which is the end of the 2 points ending the line divided by that. What is the ratio of this thing? It is very, very small, right? Once you go to a circle, you can think about the perimeter divided by the area. That's going to be, and we will do this proof more rigorously later. It's going to be a certain value. Now you can go to a sphere and look at the surface area divided by the volume. And you can keep doing it as you increase the dimensions. Turns out in very high dimensions, as the dimensionality goes to infinity, most of the volume of any sphere lies on its surface. This is really bizarre, but it's true. Almost everything lies on the surface, which means that when we calculate this integral, it will become clear. One moment. When you are writing this integral, what you are saying is how thick should the surface be? And what I'm saying is that if everything lies on the surface, it doesn't matter how thick it is, because it's all going to be on the surface. Go ahead.
But we have different units.
Yeah, we'll do this very mathematically. Yeah, we'll do this mathematically. But for now, what I'm saying is I'm being rigorous and defining it as a probability density, which is defined this way, but later I will show to you that we don't have to worry about this magnitude of delta E in statistical mechanics because it becomes irrelevant in the thermodynamic limit. That's actually a very nice proof. High dimensional spheres are actually very interesting. So they show up a lot in all sorts of things. Yeah, we will talk more about high dimensional spheres later. I'm kind of obsessed with them. So we did say, before we call this a probability density, we have to check a few things, right? We said a probability density must be more than equal to 0. Is that the case here? Omega is positive. The number of microstates is positive, right? So P nu cannot be negative. So clearly, P nu is more than equal to 0. But we also need to check whether summation nu, P nu, if we sum up the probability over all possible microstates, it should sum up to 1. Otherwise, we have an issue. Is this equal to 1? We have to do all possible microstates. For every microstate, we calculate omega of NVE. But that does not depend on omega. This is kind of subtle. So today, I want you to go back and think that this thing is omega independent if it's non-zero, right? Anytime we have written this, does not depend which microstate you are in, as long as it is consistent with what you had. And how many microstates do you have? This is total number of microstates. So when you do this integral, it's going to be omega NVE multiplied by 1 over omega NVE. Therefore, it is 1. Okay. So next time I will start with this page. I might forget and start further ahead of this page. One of you should interrupt me. If you don't interrupt me, I will start ahead of this. Okay. So think about this. Chandler talks about this. So we are following Chandler books very closely for StatMech. Okay, very, very closely. Please read that book. It's a very light book. You can carry it wherever you want. I carry it to faculty meetings sometimes because they can get very boring. So just read Chandler's book or things like that. So think about this, and we will start from here next time.
The probability of some state nu though, given some initial state, like nu1, is not going to be the 1 over omega rate.
What do you mean initial state?
Like I look at the cup, I see the microstate, and I close the cup.
But then it's not an isolated system. I'm talking only about isolated systems. You cannot look inside it, it's isolated.
No. First I look at it, then I put the cap on, and now it's isolated.
Whatever you did before that does not matter. I'm talking only about an isolated system. If you did something before it, then how was it? You are talking about opening an isolated system. What does that mean? But it's not isolated. What I'm doing here won't apply. Okay, so we have to be very rigorous in what we're
This
doing here.
is, but the definition will have some issues when you go into quantum systems. right?
It will be very rigorous. Don't worry. We will make some quantum corrections sometimes in a sloppy way, but we will be consistent.
Because when you're observing, you can't isolate it or not isolate it. So when
Sure,
you're-
sure,
you're
sure,
making an observation.
Sure,
of
sure. So an isolated system can never be created in reality, right? But it is a limit that we can aspire to. Everything else that we do will come from Taylor series of this omega and some sort of perturbation. Go ahead.
Why do you assume isolated system should be small? Maybe it should be large enough so I can be inside with a capital here.
Then I cannot talk to you again. You are isolated. You're gone. You're dead. You could go inside, but I have no way of communicating. Okay, see you next time.